Hi everybody, and welcome back to another edition of the BTSS seminar. Today we have Davide presenting on forecasting with large language models, and with Philippe for formal discussion. Thanks both for joining us. Davide, let's get going.
All right. Thank you, Michele. Thank you for inviting me, and thank you, Philippe, for taking the time and agreeing to be a discussant. I'm very grateful. So this is a project joined with Andrea Carriero from Queen Mary, and then a colleague of mine, Shubhranshu Shekhar, who's a computer scientist by training and is in the business school at Brandeis here in Boston with me. So as I was just telling Michele and Majid earlier, this is a paper that we started working on maybe 6 months or so ago, or even 9 months now, started as our own interest and curiosity on testing how some of these large language models perform in time series forecasting. So it was a great learning experience, and we learned quite a few things along the ways, and there's a lot more to learn as this field is moving so quickly. So I'm gonna try to share with you what we learned so far and where we think we want to go next. And I look forward to your comments and questions. So let me get started here with a quick intro. You probably don't need much of an intro on large language models, but among the many things that people do with these large neural networks, one of the tasks people are interested in exploring is forecasting. So here I have just a couple of pictures from articles that I have been reading, and these two draw my attention more than others. On the top right, this is a joint study between a number of universities, including MIT and UPenn, on testing how an ensemble of large language models can help predict binary outcomes, like who's going to win the elections in the UK, what's going to happen in a particular soccer or football games. Questions from many different fields, comparing the accuracy of an ensemble of LLMs against human judgment. So you probably heard before about the wisdom of the crowd idea, and so I suppose you can think of these as the wisdoms of the LLMs, how you combine them together and whether they can be accurate, and it appears that they can in this study. And then another article that drew my attention was on how a study done by UCLA looked at how LLM models can be used for accurate weather forecasting. With that sort of quick intro, again, you've heard of large language models before. We all use them. They're sort of becoming part of our daily work. We use them for sometimes summarizing text, generating text. People have used them and use them for sentiment analysis. Some of my students like to use them for code generation and completion in problem sets. I'm sure you have some of the same challenges on how to best figure out how to integrate these LLMs into our everyday life. And of course, you have the chatbots and the conversational AI that are popping up in many places. So what the paper focuses on is an even more recent development than LLMs, and something that I'm going to refer interchangeably throughout the talk with either time series language models or time series foundational models. I'll be specific in a second why I use both ways of characterizing this. So a foundational models is just a large scale, very high dimensional, general purpose model, like a neural network in these cases. So train on a very large corpus of data and used the idea is that useful to answer and help with many different tasks that are, so they're just, general enough as a model that you can use it in many different places. I like to also refer to this as time series language models because the architecture and the build up of these models very much resembles and is inspired by these LLMs. So there's the same type of architectures with self-attention mechanisms and various layers of multi-head perceptron. So sort of the same setup and same architecture as a starting point. So they build on the same architectures, these time series language models, and they are used or can be useful to uncover nonlinearities in time series data and potentially do things as classifications and forecasting and data augmentations like filling missing values, for example. So a number of features, a number of tasks that as time series econometricians we often deal with. Forecasting is going to be where I'm going to be focusing my attention in these talks. And before I even get to that, let me just highlight here what I have in mind here with these time series language models. So there's a number of them that have already been productionalized and publicly available. You can download the codes from their GitHub repositories. You can play with them. You can test them out on test data or real data. As you can see from the slide here, I listed 7 of those. They're all very, very recent. All the ones that I have here are from early to mid 2024. And some of these models are being developed by universities and private labs. Others are being developed by companies, like, for example, the Kronos model that you see down here has been developed by Amazon. Moirai has been developed by Salesforce, Tiny Time Mixers by IBM, and Times FM from Google. Nixtla is a private company that has been developing Time GPT. And by the way, this is the only one that is not publicly available, that you sort of have to go through an API to be able to run this. And so, like I was saying before, there's more. This is a good representative list of what these models are. And I'm going to be telling you a little bit more about these ones. And I'm going to be testing out most of these 7 models in what I do in the paper. So if you go through the papers of these 7 models, you're going to see, in addition to the descriptions of the setup, the architectures, the data used to train the models and all that, the descriptions of the number of very general tasks that the authors are able to accomplish with these models. Now, one big important distinction between large language models and time series foundational models is that, as I will talk about in a minute, these models are trained on data. And so the training set is a large universe of time series from many different domains, many different frequencies. And so that's a big difference. And that's where I'm going to spend a lot of the time in the early part of the talk to just highlight the differences and the way that these are done. And so what are we going to do in this paper with this time series foundational models? We're going to try to answer 2 questions. The first one is how useful these models are for macro forecasting, with the exceptions of maybe the Kronos paper. really, these papers have not looked into macroeconomic forecasting the way that we often look at. So that's the first question. How useful can this model be for macro forecasting? So I'm going to focus on something called zero-shot forecasting, which is basically an exercise where you take this model as they were pre-trained. No updating of the parameters. So you just take them as they are. Again, kind of building on this notion that they are general foundational models that can be used successfully for many different tasks without having to retrain them. And so I'm going to be focusing on this throughout the papers, zero-shot forecasting. Even though we have some preliminary results, I don't have them in the slides yet, but we found so far that when you fine-tune these models, which basically means you update the parameters to be maybe zooming in on a particular data set of interest or some features of interest, we find the fine-tuning does not seem to make a big difference, at least in what we have been able to find and do right now. So that's the first question. How helpful are these models for macro forecasting? And then the second question is, okay, now relative to existing state-of-the-art macro time series methods like vector autoregressions and factor models, how do these time series foundational models compare? So it's an empirical applied paper, and these are the two main questions that we go at. I'm just gonna highlight one important caveat as we go through this, is that there are some real challenges in using these time series foundational models for forecasting. I highlight here two things that are very much related to each other. Data leakages, as people like to refer to, the problem that these models might actually have seen already some of the data that you're interested in forecasting, potentially. Why? Because it's non-trivial to run and update these models. So it's expensive, time intensive, and really non-trivial to just develop the skills necessary to retrain these models. So often what people do is that they do exactly what we do. They take the models as they were trained at a particular point in time, and they use them for forecasting. And that's okay as a forward-looking exercise. But if you want to do this sort of backtesting or pseudo real-time forecasting exercise that often we're interested in doing as time series econometricians, this is not something that is going to be immediately straightforward and transparent. So just something to keep in mind as I'm going to go over the results, and maybe I'll point to it a couple more times along the way. Should I keep going, or yeah, all good? All right, so let me just very, very quickly, in case I don't get to spend a lot of time on the final results and the final few slides of the talk. Let me just very briefly give you a summary of what we do in the empirical part. So we do this pseudo real-time forecasting exercise on macro monthly data. We use the FRED database in our exercise. That's a database that has, in case you're not too familiar with it, more than 120 plus monthly time series. These are updated regularly by the St. Louis FRED, and they go from measures of price, output, exchange rates, financial activity, covering a very large spectrum of macro time series. So we're going to be looking at all 120 plus of these monthly time series over a time period that goes from the mid-80s to 2023. And we're going to be looking at point forecast up to 12 months out. And so I'm going to use the root mean square forecast error to summarize the accuracy of these models and the relative accuracy. So two main takeaways. I suppose you could say not all of the time series foundational models are born equal. Some do better than others. So when you take these models, you apply them to this FRED database, and you do a pseudo real-time forecasting exercise, again, with the caveat that I mentioned earlier. When you compare their forecast accuracy against the standard AR1 benchmark, you find a couple of these models, the Salesforce the model developed by Moirai and the models developed by Google times FM, perform better than the others. They also tend in general throughout all of them to perform better when dealing with less persistent time series. I suppose that makes sense, right? So these models are learning patterns, repeating patterns from historical data. And so they're better at dealing with things that are repeating patterns that have some sort of structure than time series that are less persistent and more random walk type behavior. So that's one thing. The other thing is that we find that in general, these models tend to be, while on average competitive, they tend to be at times less reliable and prone to make some unreasonable forecast for some of the series in ways that we haven't been able to completely pin down. We didn't find anything systematic to say, okay, this is why this is happening. So we find that sometimes they hallucinate and they generate forecasts that are not too sensible. So that's one of the takeaways, so sort of how they do in absolute terms. And then when we compare their performance against the BVAR and factor models, we find that they're more or less on the same, again, on par. And again, that feature I was describing a second ago of stability, they tend to be less stable and at times unreliable compared to the more stable and well-behaved BVAR and factor models. So that's the story that we take away from this. All right. So let me jump in and get to the rest. So I'm gonna tell you a little bit about these models and their relationship with the large language models architecture. I'll focus here on exactly that big difference that I was highlighting to earlier, the fact that these models are trained on data as opposed to text, as traditional LLMs are. Then I'll very briefly tell you about the econometric models. There's nothing new about the econometric models. We work with a couple of Bayesian VARs and a factor model, so I'm just going to very quickly summarize those models, and then I'll get to the empirical application, where in a bit more details I'll show you a few pictures and tables summarizing the performance and the results that I just quickly highlighted, and then I'll finish. Okay. All right, so let me get into the first part here of the talk. I'll tell you a little bit about this model. So this is going to be a very high-level description. I will not go too much into the details, but I want to try to sort of build some understanding of how this model works, using a setup and a framework that's very much what as time series econometricians we're used to think of. Before I even do that, let me quickly tell you about some of the other papers out there that we have uncovered while we did our research. So first of all, it's challenging to do a literature review on a quickly expanding and exponentially growing field. But one thing that we certainly have seen, one kind of common theme, is the fact that these models for this time series foundational models have kind of gone through a couple of phases. The very early on phase is what I refer to as the prompt-based methods. This was an early attempt to use pretty much large language models as they were, just with no additional work on these, and just feeding questions related to forecasting or classifications pretty much in a prompt-based style. So you could imagine, for example, taking a time series of inflations and translating that into a paragraph that says inflation was this in 1974, January, and that, and so on and so forth, and then feeding it into the model. That's the most basic way of prompt-based forecasting. There's more sophisticated way of doing it as well, but sort of high level. The early approach was very much let's just take those large language models and use them as is for time series forecasting. And then the second phase is the one where a number of people realized the disadvantages and the limitations and the inefficiencies of doing it these ways, and took some steps to retrain or change some of the components or play a little bit with the setup so that you could actually feed data in the training phase. And then the references here that I have under here are more or less the ones that I talked about earlier when I was telling you about the different time series foundational models. So this sort of big distinctions between how this thing has evolved very quickly. As you can see, this is all happening very fluidly over a very short period of time. We noticed a few papers applying large language models or time series foundational models to macro and finance questions. And most of these papers, here we listed 4 of them, are on financial data and financial applications. So this is an example of taking a ChatGPT framework, building it, combining it with Wall Street Journal's articles in a sort of fine-tuning type exercise to predict financial and macro variables. BERT, Roberts, and OPT, those are LLM models that were fine-tuned to financial data, so they're sort of more tailored to better equipped to handle financial text, and those models were combined with Thomson Reuters real-time news feeds to predict firm-level daily returns. This is a very popular paper by Kim and others from University of Chicago, who has developed their own ChatGPT bot, an extensions of ChatGPT for doing earning predictions by kind of feeding financial statements, 10Qs or 10Ks into the chatbot and using it to predict future earnings. And then finally, probably the paper that is the closest to what we did is this paper by 2 researchers at the St. Louis Fed who used an LLM from Google to predict inflation. Again, in their paper, in that exercise, it was very much a prompt-based approach. So related to this first group of papers here, the way that it was developed, and they focused just on inflation, and they had some interesting results on that. Okay, so with that said, let me jump in and tell you a little bit about how to think about this time series foundational model. So as I was saying earlier, I think of them as a bridge between the original large language models who handle textual data in their training, and then the fact that the time series data, the one that we're interested here in working with, is numerical. So imagine that you have a large corpus of time series data, and so I call that big X, boldface X here, and so a bunch of time series from time 1 to time t, the usual sort of time series notation here. And imagine that you want to estimate a mapping called that f of theta, so that you can then use these mapping functions to forecast a new time series, call it y. And that's sort of the idea. So the goal is really how do we use all this time series data in a way to generate to estimate a very flexible nonlinear function f of theta, which we can then use to do a lot of different things, including, for example, forecasting. So if I feed a new time series, historical time series y, can I get a forecast for the future age periods of y? That's sort of the idea. And And the story really is how do we estimate this f of theta, right? So sort of before we get into how do we estimate the f of theta, let me tell you a little bit about how do we pass this high large dimensional matrix or vectors of data into the algorithm. So to go through that, I'm going to tell you a little bit about the way that the time series foundational model works. And so I'm going to focus first on this concept of tokenization, and I'll tell you about the architecture of these models and a couple of other things along the way. So tokenization is, for large language model, tokenization is the process through which a text, a paragraph, a book is broken down into tokens. Think of tokens as words or combinations of words. And how does that happen for time series data? It's the question. And so you have a quick picture to give you a sense of how this is done. So imagine I have one time series X, and that's the raw data here, X. Whatever that time series is, it could be inflations, it could be GDP, it could be electricity consumption. So the frequency doesn't really matter for what happens, but you got that time series. The first thing that you do to go from the time series to tokens, the same way that an LLM goes from a book to tokens, is that we go through a process of scaling. So because you have many different time series potentially expressed in different ways, some are expressed in growth rates, some are expressed in dollars, some are expressed in units with different scaling. So you imagine there's a first step of scaling this time series, and really think of the most basic way of scaling as standardizing the time series, for example. So you extract the mean, divide by standard deviations or something, or a robust versions of that. And then from there, different LLMs, different time series foundational models take different approaches to go from the scale versions of the data to the tokens. So the two main approaches that are out there is one is called quantization and the other is called patching. Quantization here does the following. So it takes that rescale time series and maps the values of the time series to beans. So imagine that you construct a very large number of beans, and then you basically go through a process of mapping each and every value of that time series to a bean. And so high values of the time series get mapped to higher beans, low value of the time series get mapped to lower beans. This is very high level, but just to give you a sense of how this can be done. Those beans basically are then what defines the tokens. I'll give you a specific example in a second, but that's the idea. Patching is a slightly different process. Instead of looking at the individual values and mapping them, patching divides the time series into segments. Here I try to use different colors for different segments, but suppose you define the length of a segment. The idea is basically each and every one of these segments becomes a token. And so the idea is that once you have tokens, you're sort of back to a framework and a setup that is similar to what LLMs normally do, when they just basically take the tokens, and with the tokens in hands, they try to predict what's the next token gonna be. So now that we have tokens, we're sort of in the same setup. And let me just give you a couple of extra additional details on the scaling and tokenization, just very briefly. So there's a lot more in these slides, but the key thing, as I was saying earlier, the process of scaling is basically the process of standardizing, organizing the time series so that they're all expressed in a common scale. And again, think of something very simple as subtracting the mean divided by a measure of spread, something like that. Patching. So let me tell you about patching. So here is a little example. Suppose your time series is this one here. Remember, the patching is basically a process through which you take the time series and you break it down into smaller segments. So if I define the size of the segment, the patch size, to be 3, then the first three will make up the first patch. If I define an overlap, the next group here will define the next patch, and so on and so forth. So basically breaking it down into patches, it's just a very straightforward process of once you define the patch size, organize them in this way. The quantization, same exact time series. Suppose that I define something called uniform binning. So I define 4 bins, each one of the same size. So the first bin goes from 4 to 5, 5 to 6, 6 to 7, 7 to 8. So all the same size. All you're doing, you're mapping each and every one of the values of the time series into a different bin, and your token becomes the sequence of bins down here. And so that's just two simple examples on how this process of going from the time series to the tokens happens. I hope that's clear enough. Few considerations on the tokenizations is that if you read through some of these papers, you'll see that the authors are very careful in defining, for example, the size of the patch, the size of the segments to be functions of, for example, the frequency and the type of data you work with. They find larger patches to work better for high frequency data than lower frequency data. They experimented with different type of quantizations using uniform quantization, as I just described a second ago, or data dependence, where the bin size adjusts to the sort of distributions in the data. And then sometimes they define scaling at a global level throughout the entire length of the time series, or they do it by context. And so those are sort of tuning parameters or choices, modeling choices that the authors of these papers have played around with, and just to give you a sense of how people see this. Very briefly on the model architecture, without taking too much time. Really, this is very much like I was saying earlier. The key thing of this model is really to figure out an efficient and sensible way to go from the time series to the tokens, so that you can then take the tokens and feed them into an architecture that is very much borrowed from the large language models, so from the ChatGPTs or these, so or the other models that are out there. So transformer-based architecture is the most common approach, with self-attention mechanism to capture not just the dependence between the tokens nearby, but also sort of the long the long-range dependencies, very much in the way of contextualizing the tokens with the entire time series, rather than just focusing on a narrow, limited set. Some of the models do actually use traditional MLP setups, so non-transformer based architectures. For example, is the case of tiny time mixers, which is the IBM large language models. But for the large majority, the models that we play here with are generally built with the same transformer-based architecture than the LLMs. So two things now I want to finish with before I jump into the econometric models and the results. So when people think about large language models and training these incredibly large models with billions of parameters, they have available extremely large amounts of textual data, and so that definitely helps, right? So with time series data, you have not as much time series data available to use. So often when you go through some of these papers, people figure out ways to deal with the scarcity of the data, so that they don't have to estimate models that are too small. And one of the things, for example, that the authors of the Chronos paper did, they did this thing called time series augmentations. They actually generated artificial time series data by doing a convex combinations of existing time series. So imagine this is what they do more or less. They take a bunch of time series and they fit to time series. They fit ARMA models, or they do STL type decomposition to extract the trends from the seasonal, from the cycles. And then imagine a process of reshuffling these features. So you grab a particular trend and a particular seasonal patterns, and you kind of build a new artificial time series. And imagine doing this many, many times so that you construct a universal time series that is much larger than the one you start from. I was recently reading a paper by Brian Kelly, who actually does a similar thing with Fourier transforms to a number of stock returns data, and it's sort of a process through which you increase the size of your training sample, basically. So that's just something worth pointing out about these models. The next thing that the last thing that I want to highlight is that now that you sort of have your data plus artificial data in some cases, and you tokenize that data, every single time series has been tokenized, you got all these tokens, and you got your time series model, your architecture. So this is sort of what I was telling you at the very beginning of these sections, when I was telling you about how you go from the time series to the tokens. And this was the second part that I talked about, what this architecture, what these models look like. You sort of take all these time series, you feed them into the model, and this model is returning often a probability, statements about the distributions of tokens. And so what's the probability distributions of what the next token or the next 2 or 3 or 5 tokens are going to look like? And how do we train these models? So we grab all this data, we feed them into the models, and we tweak with the parameters of the models by maximizing reward functions or minimizing the loss functions, very much like, okay, so these are the tokens, these are sort of the fitted tokens, right? And these are the weights that we're going to try to optimize over. Once you optimize, once you pre-train these models over all this large amount of data that you had available to work with, the zero-shot inference is a very simple thing where you take a new time series, you tokenize it, you feed into the model using the estimated parameters data had, and the model will return probabilities of what the next tokens are going to be. And those tokens will be transformed back and rescaled and everything so that you get basically your time series forecast. That's the idea. And so one last thing about this particular thing that I just described, zero-shot inference after the pre-training of the models and the fine-tuning. What is that? So in the pre-training and zero-shot forecasting, what you do, you take this large amount of data, you learn the general patterns after you tokenize it using self-supervised techniques. You get your estimated parameters, and then you just do what I just described. You take a new time series, you feed in, and you forecast. So imagine that, like in what I'm about to talk in a few minutes, I train these models on a ton of different data, and now I'm going to feed a bunch of macro time series. I'm going to ask the models to forecast the next 12 values of this macro time series. One could take a step further, and instead of doing zero-shot forecasting, it could do this thing called fine-tuning, where what you could do, you could take the estimated weights and parameters from the pre-training phase, and you could try to fine-tune those parameters so that the model works particularly well for a specific task that you're interested in. If your specific task is macro forecasting, maybe you could feed a bunch of macro time series to the pre-trained model, and starting from the estimated parameters of the pre-training phase, you could sort of iterate and see if you converge to something that is more tailored to the specific needs that you have. And so that's sort of the idea of fine-tuning. Like I was just saying earlier in the introductions, in this paper, I'm going to tell you about everything that we've done is on zero-shot forecasting. So these models have been actually pre-trained by Amazon, Salesforce, IBM, Google. We just take them with those parameters, and we just use those for forecasting, and that's what we do. But we're also doing, for two of these models, for the Google models and the Moirai models, we're actually fine-tuning them as well. And that's something that we have been carrying out. And we're not finding a big difference so far, but you could sort of imagine that to be a much more refined way of doing forecasting. Last slide before I move on. I have more in the paper, but just to give you a big description, a kind of a quick summary of all these models. So those are the 5 models, 2, 4, 5. So LagLlama, Salesforce Moirai, TinyT Mixer of IBM, TimeGPT of Nixla, and TimesFM of Google. This is the release date. This is all the data these models were trained on. This is the size of the models, of the data that went into the training of the models. And some of these models are univariate, and a couple of them are actually multivariate. So just a few details. What I want to highlight is that you see 3 of these models. There's a little star. The star actually highlights that these models were trained using Fred and D data as part of their training. So again, in this data leakage type point that I was trying to make earlier, sort of something to keep in mind, right? So even though, I mean, they have seen the data that we're about to test the models on. Truth to be told, they've seen that data together with a lot of other data. And so how much weight they put on that is not necessarily, going to bias things too much, but it's certainly something to keep in mind. You can imagine the fine-tuning exercise of just telling these models, okay, now we just focus on this macro time series data and see how much the parameters change when you do that, and the forecast improve. All right, that's all right. So on the econometric models, I'll go very quickly, so I'll have 10 minutes or so to tell you about the results. So we compare this time series foundational model against 3 econometric models. So the first one is a multivariate Bayesian VAR with natural conjugate prior. So that's just a VAR. So imagine we take all these 120 plus macro time series, put them in a big vector Y, write a VAR for them, use some sort of conjugate priors, use some sort of sparsity inducing priors to push, well, to kind of, a little bit, regularize the high dimensional model that you're about to estimate. And so Minnesota style priors, as it's often done in macro time series forecasting, normal inverted Wisher priors that are conjugate and so don't require a lot of computations to estimate and update the parameters. We augment these priors with a couple of tweaks that are helpful, often as work by Giorgio Primiceri and Domenico Giannone have shown, to forecast, especially at longer horizons. So something called sum of coefficients or single unitary priors, to avoid that the deterministic components of these models weigh too much and take over in the forecast. And the Minnesota setup with this natural conjugate framework allows one to estimate these models without MCMC methods. And you can also get marginal likelihood in closed form, which allows you to optimize the hyperparameters of the priors. And so those are all sort of the things that people working with large Bayesian VAR have found to work well in macro forecasting. The main challenge, limitations of this sort of Bayesian VAR is that they do not allow for cross variable shrinkage. Cross variable shrinkage meaning that some of the variables in an equation can be shrunk more heavily than in another equation. And that's something that people have found to be limitations and sometimes affecting the accuracy of the forecast. So Chen developed a setup to allow for symmetry in the prior while keeping conjugacy. So before this paper in quantitative economics by Chen, one would go the MCMC route to estimate a model with asymmetric priors and sort of get out of the limitations of the natural conjugate VAR setup. But it would take more time, and especially with many variables like the 120 we're experimenting with here, it's sort of complicated. Joshua Chan wrote cleverly this down in a structural VAR format, and through that allowed to do an equation by equation estimations, allowing for asymmetry in the priors. So that's just an interesting variations of that initial VAR that we also wanted to add to our pool of models, because many have found that asymmetric priors are helpful when it comes to forecasting macro data. Both VARs, by the way, have constant volatilities, constant variance covariances. We did not allow for stochastic volatility, mainly because we were focusing just on point forecast in this exercise. And then the last of the models that we compare against is a factor model. So this is very much implemented the same way that Mike McCracken and Serena Eng did. We basically take all these 120 time series, they transform them to make them stationary. They use PCA with the expectation maximization algorithm to deal with missing values when present. They estimate a few factors. They take the first of the factors, sorry. Oops, I don't know what's happening. Okay, my mouse is. They take the first factor estimated, and then they run an augmented distributed lag model where they regress each and every time series on its own lags and lags of the factor. And then they do a direct forecast. So for every different horizons that you're interested in forecasting, you run versions of this model. 12 different versions if I want 12 different forecasts. And then for each of every one, I just basically project forward and generate my forecast of interest. Again, these two models here are multivariate. So in a single shot, I'm forecasting all 120 variables. These, I'm just doing it one variable at a time after I extracted the commonality across those variables from the PCA step. That's the idea. Setup for the empirical application. So as I was just saying earlier, we grab this Fred MD database available at the Fred St. Louis Fed. The data is monthly from 1959 to December 23, covers about 120 plus key macro variables, including output prices, interest rates, financial quantities as well. Both equities and fixed income financial variables. We split the sample about in. We said like 25 years of data to kind of warm up, pre-train the models, and then we go from that point onward all the way to the end of the sample. In what I'm about to show you here, we stopped in December 2019. In the paper, we have results going all the way through the COVID period and the post-COVID period. But just so that the stories are similar, they change a little bit, where the time series foundational models work a little better over this most recent period. Here, I'm just going to focus on this longer span of time covering all the way to the pre-COVID. So just me highlight how this thing we do it. So for the three econometric models that I just described, so we're doing the traditional pseudo real-time forecasting, where I'm just going to feed the data to the model all the way to a particular point in time, and then I just estimate the model and forecast. I do the same thing for the factor models and all that. For the foundational time series models, I can't really do that. It would be too prohibitively too expensive to do it this way. So we just basically take those models as trained, and every time we feed the data up to a point in time, and we say, give me my forecast for the next 12 periods. So the issue that I was mentioning at the beginning about data leakages, it sort of comes into play here, right? Because I'm not retraining the model only using data up until a certain snapshot in time. I'm actually just using those pre-trained models. So that's that consideration that I was doing. In the paper, we focused on doing this whole exercise for VARs and groups of variables that go from about 20 to 40 to 120. So we sort of build into phases. Everything that I'm going to show you here in the paper is in the slide, sorry, is based on those 120 variables. So it's what I refer to as the X large system, and it's just basically all 120 plus variables. All right, so how do I evaluate? After I generate the point forecast for the VARs and the factor models and the time series foundational models, for each and every variable in these 120 pool of variables, I'm going to compute a root mean square forecast error over the period from 85 to 2019. And I'm just going to divide that. I'm just going to compare that to the forecast accuracy or the forecast errors of the benchmark, which is an AR1 in our case. So we're going to construct a variable model horizon specific ratios. So we're going to be able to see variable by variable, horizon by horizon, model by model, how they perform relative to an AR1. Like I said, I'm focusing just on point forecast. So for the VARs, which generate density forecasts, the Bayesian VARs, we're just going to take the median. The factor model just gives me a point forecast, so just grab that. For the time series foundational model, some of the time series foundational model, remember earlier I was saying these models are probabilistic. They actually give you probability over tokens. So for those that actually gave me the probabilities, we simulate these 1,000 times to get many different tokens, and then we grab the median of the forecast generated. In some other models, we only directly get the median, and so in that case, we grab the median. Some others just gave us a single path, and that's what we took. And so try to keep the comparisons as fair as possible, accounting for the probabilistic natures that these models have. All right, so now I'm just going to show you with the last few minutes a couple of figures and a couple of tables. So the first figure, so I'm going to try to answer the two questions that I had at the outset. So how do these models compare? So we have those 5 different foundational time series models, and I want to see over those 120 series, how do they compare to the AR1 benchmark? So this is a slide that gives you a summary of that. So it's broken down into 4 panels. This is 1 month ahead forecast. This is 3 months, 6 months, 12 months. In each case, what I have here is a straight line and 1, which is basically, showing relative benchmark points. And then box plots for each and every one of the 6 models we experimented with. So lag llama, 2 versions of Moirai, small and large, tiny time mixers, time GPT, and times FM. So as you can see with the box plots, the median over those 120 variables, this is how I compute the box plots. Over all 120 variables, the median root mean square forecast error ratio is slightly above 1, so slightly worse than an AR1 benchmark. Slightly above 1, slightly below, above. You see how wide some of these box plots are. We removed showing the outliers here because in some cases, what I was telling you earlier about the instability of these models, they actually completely blow up the scale. As you can see, 2 of these models, times FM, the green bars, and Moirai large, the yellow ones, do a little better. So in what I do going forward, I'm just going to focus on those 2, and those are the 2 that I compare against the VARs and factor models. So that's sort of, in absolute terms, I take those 5 models and 6 models, sorry, and I compare them against the AR1. What do I find for those 120 variables at 1 month ahead, 3, 6, 12 months ahead? I got a table here that summarizes the same results. The median of those 6 models at different horizons. This is the median root mean square forecast error. So you sort of see the numbers that earlier I was just showing you as a line in the middle of the box plot. But I want to highlight that the max root means square forecast error ratios for some of these models is huge, right? So you can see kind of the thing I was just telling you earlier, that for some variables, the forecasts are just completely off. And so that's something that adds a little bit to the complexity of the study here. Question. All right, so that's kind of the key takeaways I was just mentioning. I suppose recommendations: use this with cautions. It's just a. All right, so here is the comparisons of those 2 best performing time series foundational models. So they are down here in yellow and green, against the 2 VARs and the dynamic factor models. And as you can see, by and large, they perform similarly, right? With perhaps the VARs and the factor models specifically doing better, a bit better. In some cases, the differences are statistically significant. In other cases, in most cases, they are not. So I suppose you could say on par with those models, and a bit more stable. And this is something that you can see again from the same type of table that I showed you earlier, where you can see where the VARs tends to have a bit more stable results, for sure than even those 2 best performing time series foundational models. You can see down here, the max root mean square error is close to 1.5. It's a bit smaller for the BVARs, and not as much for these and the factor model. So that's sort of the key story. So I guess if you jumped into this as I did, as a time series forecaster, worried that LLMs would soon take over, we're not there yet, but we're sort of in a situations where we're getting comparable answers from these models. We did a few other things. I think I'm running out of time, so I just want to highlight one thing that I mentioned at the outset. How do these models work with different type of time series? So we looked at various slices of the 120 variables we have been playing with. One key thing that we saw was important, that we saw some significant difference, was the breakdown of organizing the time series by the degree of persistence. And if you take the more persistent ones, these are the ones that have transformation codes in the data equal to 1 or 4, which basically means they were either kept in level or they were just taking the log off. And those appear to be time series that have higher degree of persistence because they are not first differenced in any way. And here you can see that the BVARs and the factor models particularly do better than you see some larger discrepancies, especially at one month ahead. You can kind of see that times FM and also Moirai, they are significantly constant. I mean, they're almost entirely above the 1 threshold here. Interestingly, if you look at the less persistent ones, you see how much more comparable and better performance those time series foundational models are. And again, I guess it goes back to the point I was mentioning earlier at the outset, where I was saying how, by and large, these models, which learn very well from the data patterns, tend to do well when we're talking about time series that perhaps are more in the style of repeating patterns as opposed to trending and unstable ones. So I wanted to finish with that. So let me just conclude. So I've tried to give you an overview of the comparative exercise we did, evaluating the forecast accuracy of these new models, time series foundationals or time series language models, comparing them against traditional state-of-the-art, well-tested out econometric time series models on these 120 plus macro time series from FredMD. So we find a couple of interesting things in this empirical exercise. So the performance of the best time series foundational models that we have seen in our exercise is comparable to that of B-vars and factor models. However, the B-vars and factor models tend to be a bit more stable and more reliable, more robust, and less prone to generate those occasional unreasonable forecasts. Lots of stuff still to do. One of the things that we have already been doing that I quickly alluded to, but we're going to be finishing off soon and update in the new version of the paper, is to do a comparisons with the fine-tuning of those best performing time series foundational model. We can certainly add more models. We were asked to consider Kronos as well in the comparisons, and it would be very nice and interesting also to take a look at density forecast to the extent possible. All right, we can stop here.
Thanks, Davide.
Yeah.